A growing need for public security has risen in recent years, necessitating the use of baggage checks at venues for large-scale events or gatherings. In many cases, however, the cost of specialized tools such as X-ray scanners or metal detectors, or the need for increased manpower to perform manual checks might not be cost-effective or feasible. To combat this issue, we introduce a system for performing in-bag object detection using readily available Wi-Fi devices. Leveraging the fact that Wi-Fi signals can easily pass through the materials that bags are commonly made out of, like cloth, and that different materials such as metal or water can reflect or absorb those same waves by varying amounts, we can use off-the-shelf Wi-Fi devices to broadcast and receive a wireless signal after it has passed through an object whose material we wish to classify. By reading the channel state information, or CSI, associated with the signal, we can determine the signal changes caused by different materials and use a machine learning classification algorithm to determine an object's material based on the CSI received. Our capstone project design revolves around using the open-source Atheros CSI tool, which provides a patch that can be applied to the Linux kernel, enabling the reading of raw CSI data from a supported Qualcomm Atheros network interface card. As a proof of concept, we placed 2 of these supported network cards in 2 regular laptops running Ubuntu with the patched kernel, creating an environment where Wi-Fi signals can be sent and received. From here, we can put an object in between the antennas of the laptops, send Wi-Fi packets from one laptop to the other, read the CSI from the network card, perform data pre-processing on the CSI to enable classification, and feed the data into a pre-trained machine learning model to determine the material type. Now that we have provided a brief overview of the system, let's examine each aspect of the system in more detail, namely our working environment, the pre-processing of the received channel state information, and the machine learning algorithm used. As mentioned in the overview, we utilize 2 laptops, each with a Qualcomm Atheros AR9462 network card installed. Each laptop provides us with 2 antennas, totaling 2 transmitting and 2 receiving antennas. One laptop, which will be used to send Wi-Fi packets, sets up a Wi-Fi access point. This laptop runs a slightly modified version of the Send Data program that comes with the Atheros CSI tool that will repeatedly send packets on a raw socket with an Ethernet header corresponding to the MAC address of the receiving laptop's network card. The receiving laptop sets up 2 programs. One is a modified version of the Receive Data program that also comes with the Atheros CSI tool, which upon receiving a message from our main application begins accepting packets being sent by the other laptop, writing the raw data received by the network card to a file. The second program is our main application, written in Python, which controls our system workflow. It provides an interface that allows a user to start receiving packets, input data into our classifier, and output classification results. Initially, the send and receive programs require 2 people to manually start the programs. However, motivated by social distancing requirements brought about by COVID-19 and for a better user experience, the programs were modified to allow a single person to collect data. The 2 laptops are placed opposite one another, with the object to classify being placed slightly closer to the laptop sending packets. Experiments varying the location of the object showed that placing the object closer to the laptop sending packets yielded better classification accuracy. Training data for the machine learning model was collected by putting objects of various materials at the indicated spot and saving the raw data from the network card, which includes the channel state information. The data we save from the network card cannot directly be used when training our machine learning model or performing classification. First, the raw binary data provided by the network card has to be organized into a structure that is more easily accessible and readable. In particular, we need the size of the payload being sent with each packet, which for an Atheros network card is a 16-bit unsigned integer found at a 25-byte offset from the beginning of a block of data for a given packet, and the matrix of complex CSI values that immediately follows, where each element in the matrix consists of 2 10-bit signed integers for the real and imaginary portions of the CSI value. Next, we remove outlier packets in our collected data, which are packets whose amplitudes are over 3 standard deviations away from the mean amplitude of each subcarrier, and packets collected by the receiver where the payload length was not equal to the payload sent by the transmitter. As a result of the Atheros network card not properly calculating the CSI phases due to being inherently uncalibrated, we must also apply a linear transformation to all remaining packets, otherwise known as phase correction. This phase correction makes it so that for a given subcarrier, the real and imaginary values are similar across all packets without altering the amplitude of the CSI value, allowing us to extract more information from each CSI value that can be used to train the classifier. We also subtract the CSI values from the second receiving antenna from the CSI values of the first receiving antenna of the laptop to better capture the features of the material. With the data preprocessing completed, we now have CSI values that provide distinct features based on the object material. We can break the CSI values up into their real and imaginary portions to use as features to train our machine learning model. Specifically, we compute the real and imaginary means, real and imaginary medians, and real and imaginary standard deviations to use as features. We use the support vector machines algorithm, also known as SVM, to classify different materials based on the CSI values extracted from performing a test. To train the SVM model, we first performed several tests on many different materials. To make this dataset larger so that it can be used to both train and test the SVM model, the packets received from each test were split up into collections of 1,000 packets, with a 500 packet overlap between samples. The resulting dataset was divided into 60% used for training and 40% used for testing. We then performed additional trials on materials in bags to test the SVM model. The resulting accuracy was 96% on 8 different materials, which included styrofoam, wood, paper, metal, leather, plastic, glass, and water. We found that the model performed best when trained on CSI values of different materials while in a bag, but did try training on materials outside of bags and materials both outside and inside of bags. Finally, we provide a quick demo showing off the system we have described in this video. Here, we first place a glass object inside a bag to show that we indeed can classify an object's material while it is visually obscured. Next, we use our main application to begin receiving packets. The program has been pre-configured to receive 10,000 packets as a remnant of our training data collection process, although the number of received packets can be reduced to speed up classification time. After the packets have been received, the data is passed to a classification server also running on the laptop that will classify the material. While this process may appear to be slow, it is also a consequence of receiving 10,000 packets, and can likewise be shortened by receiving fewer packets. We will see that the classifier correctly outputs the material of the object as glass, which concludes our discussion of our capstone design project. Thank you for watching.